Hello, good evening, everybody, and thank you so much for joining us at tonight's Cafe Sci. My name is Sarah Grummett, and I'm honored to welcome you all this evening. Cafe Sci is presented by PPG. Cafe Sci is also supported by good people such as yourselves. Thank you to everyone who donated to support this program. If you're unable to donate but would still like to support Cafe Sci, the most helpful thing you can do is to invite your friends to join our audience. Cafe Sci typically takes place the first Monday of each month, and you can register for next month's speaker at carnegiesciencecenter.org. Tonight, we are thrilled to welcome all conference attendees and Cafe Sci guests to this special event in partnership with the Pittsburgh Quantum Institute, PQI. Now, it is my pleasure to introduce Distinguished Professor David Snoke, co-chair of PQI, who will be introducing tonight's guest speaker. Professor Snoke is a distinguished professor at the University of Pittsburgh. His research group uses a wide array of optical methods to study fundamental questions of quantum mechanics and in semiconductor systems. Professor Snoke has received numerous awards, including the APS Outstanding Referee Award in 2016 and being named a Fellow of the American Physical Society in 2006. Please join me in welcoming Professor David Snoke.
Well, thank you, everybody. And I want to especially thank Allan for being here. Some of you know we had some change of plans in the past few weeks, and Allan was extremely gracious in coming at short notice. One of the things to point out about this event is that it's also part of the UNESCO Year of Quantum Mechanics. They have designated the whole year of 2025 as a celebration of quantum technology, and that's partly acknowledging that quantum technology is really becoming a big thing. And we heard a lot today at the technical sessions about what's going on with that. So just to give you a little bit of background, I've known Allan for many years. He is the Sid Richardson Foundation Regents Chair Professor of Physics at the University of Texas at Austin. He's won better prizes than me. He's won the Buckley Award for Solid State Physics and the Wolf Prize just recently for something that lots of us at the technical sessions are very aware of with the twisted layers of two-dimensional materials. In general, Professor MacDonald has had a long career in two-dimensional materials. Some of you may be familiar with how we talk about space-time as having 4 dimensions, not just 3, and that leads to all kinds of interesting physics and thinking about what does it mean to live in 4 dimensions. Well, you can go the opposite way, and actually really strange things happen when you go to 2 dimensions, and so he's going to talk to us about that tonight. So let's welcome Professor MacDonald to come and give us this spot. Oh, yeah, you have them like this.
Can people? Okay, now. Okay, so thank you. It's a great pleasure to be here and to speak about quantum physics for the year of quantum, as David mentioned. My grandson learned that I was coming to Pittsburgh this week, and he prepared for me told me how I should begin my presentation. And this is what he wrote. It was what he came up with, with some help from ChatGPT. Xander's mom is actually from Pittsburgh, and she proofread this and says that at least the part about the parking spaces is true. So it's a great pleasure for me to be here and talk casually about quantum science, what I've done all my life, and and especially in this program in association with the Pittsburgh Quantum Institute. I start every morning with a cup that says PQI on it that I picked up on a seminar visit. It's just the size I need in the morning. So as David mentioned, I'm a substitute tonight, and you would have heard a beautiful talk from Bill Phillips from NIST, if not for some of the upheavals in the science world, science funding world that you've been hearing about on the news in recent days. And since I'm speaking to a broader audience than I normally do, I want to see if maybe I can convince at least one of you to write a message to your congressman and complain about politicization of science funding. And I also want to say that, another thing that actually goes back to previous administrations is that we are in danger of this country of becoming less welcoming to foreign-born scientific talent. I'm particularly thinking of the China initiative, which some of you may have heard of. Initiatives like that do not serve our country at all. And I hope that you can make that point to influential people. Okay, that was my main message. So Bill Phillips is an expert on the quantum mechanics of atoms and the quantum mechanics of how atoms interact with light. This physics, the field he belongs to, atomic, molecular, and optical physics, as we call it, AMO physics, really builds and does incredible things based on an exquisite understanding of the quantum mechanics of atoms that I'll mention in just a moment, and how quantum mechanics, atoms interact with quantum light. So I'm from a different field, and I'm going to speak about my field. I'm going to talk about the quantum mechanics of the solid matter that surround us in our everyday life. And so this is a different field from atomic physics. This is a famous remark about solid-state physics made very much in its prehistory by one of the pioneers of quantum science, Wolfgang Pauli from ETH Zurich. And so he said, solid-state physics is dirt physics. And what he was referring to was the fact that many of the solids people were working on, they could not measure reproducible properties. So if you can't measure behavior reproducibly, then it's hard to start building an understanding. And it's exactly what Pauli was actually referring to is exactly the same thing that we have now built semiconductor technology on. Some solids have properties that are exquisitely sensitive to details, and our semiconductor technology only works because we can make wafers of silicon with only one mistake out of a billion or so in terms of the atoms we place in that material. So I'm going to try to cover three things. First, I'm going to, many people in this audience are experts on quantum mechanics. Many are not. So I'm going to just say a few things about the basic properties of the quantum world, and just generally how we use that theory. What's the nature of the enterprise of understanding the properties of materials, and as I'll explain, they can only be understood with the quantum description of the world. And then I'll give a few examples from, relatively modern physics. Okay, so this is I'm going to talk about what is perhaps the most important property of quantum mechanics, which is quantum parallelism. It's very non-intuitive. So in the classical world, if you're a person, You might be MAGA, or you might be woke, or you might be somewhere in between, but you're something. And but in the quantum world, the state of matter is state of a person, let's say, is expressed as a mathematical object called a vector. And we use these funny little symbols for vectors, putting a straight line on one side and a line on the other side, and we call it a ket, okay? And so a quantum state is actually a sum of two vectors, one for two different classical states. So you're at the same time, a quantum state would be literally MAGA and woke at the same time. So I think there must be something in there that might cure our political ills in this country, if we can only figure out how to use it. Okay, so that's one important thing about quantum mechanics, and I'll come back to it, that really bites in materials, as I'll explain in a moment. Here's another very important thing about quantum mechanics that we call wave-particle duality. So a quantum mechanical state of a particle is not at one position or another position. In the same way, it's at every position at the same time. And the state is specified by a number associated with each position. And so that means that a quantum mechanical state for the degree of freedom, as we say, of where is a particle, is a wave. A wave, just like a sound wave or an ocean wave, it's everywhere at once, okay? It moves through, okay, so I shouldn't say that. So here's a picture of the solar system. You all know. Planets, big heavy things, move around the sun. You may remember, if you've taken a physics course, that these planets are attracted to the sun with a force that goes like 1 over the square of the distance of the planet from the sun. And if you plug that into the mathematics, it turns out that explains the fact that planets go around the sun in approximately circular orbitals. But in quantum mechanics, if these particles were quantum, and actually they are quantum, everything is quantum. We know quantum theory is the fundamental theory. Then the planets would be everywhere around their orbit at once. And the planet wave, has a wavelength which is related to the velocity of the planet. Actually, what appears here is the mass of the planet times its velocity, which is what we call momentum. I'll refer to in a moment. But so the wavelength is Planck's constant divided by the momentum. And what is Planck's constant? It's the one new number about nature that defines the quantum theory. So this number, it turns out, compared to our human scale, is a very short wavelength, a very small number, so that a big massive planet moving around the sun, we don't notice its wave character at all. Now, if we come to an atom, this is Bill Phillips' realm, the way an electron moves around a nucleus in an atom is the same force law. Opposite charges, electrons are negatively charged. The center of the atom, the nucleus, is positively charged. The force law goes like 1 over distance squared, same as in planetary motion. But a single electron weighs much less than a planet. And that means that the wavelength is actually comparable to the size of the atom. And it's actually the wave character, the fact that if the atom is a wave that's everywhere around its orbit, that wave has to return to its same value once it goes around the orbit once, has to be a standing wave. And that's what leads to, you can only have an integer number of wavelengths, and that leads to the quantization of the energies in the atom. So in an atom, in our solar system, the fact that we have a bunch of planets with different orbits and different energies in those orbits is just an accident of the evolution of the solar system. But in an atom, it's a fundamental law that the only possible orbits for the particles are a certain set of discrete orbitals characterized by how many wavelengths fit around an orbit. And so those are those are the only two equations in my talk, and we'll come back to them. These are the most basic ideas to quantum mechanics. Okay, so now I want to talk about applying quantum mechanics to matter. And the simplest type of matter is the matter I'll talk about, which is crystals. I think you all know that, it's common for matter to crystallize. Normally it's the lowest energy a naturally occurring state of matter at low temperatures. And in a crystal, the distance from one atom, one atomic nucleus, to another one is repeated indefinitely. So all of the atoms are equally separated from each other. And there's a special property of waves that occurs when they can scatter off something that repeats in space. So here's, this is another version of the same equation I showed you before, and it says that the momentum, mass times velocity, change for an electron when it, scatters off this a bunch of nuclei that are completely periodically distributed, is given by, it's proportional to Planck's constant divided by the so-called lattice constant, the difference between these energy minima, which are, let's say, located at the position of the nuclei. So in a crystal, this is the first thing you learn if you take, a course on the quantum mechanics of crystalline matter, is something we even call a theorem because we think it's important. It's called Bloch's theorem, and it says that the momentum can only change by fixed amounts. And so that means the momentum, if you imagine fixed amount being 12 hours, the momentum modulo, what day it is, the momentum cannot be changed in a crystal. And that means that particles in a crystal, which you might think would bounce around like a billiard ball, with all of these heavy nuclei in the way, actually move like they're in free space, and that also has a lot to do with silicon technology. Now, this. As I mentioned before, according to quantum mechanics, an electron in a crystal is a wave. It's everywhere at once. And but there are many electrons in a crystal, and they're all everywhere at once. And what this is indicating is that when they're close together, they interact strongly with each other, because they're like charges and they have repulsive interactions. And so you can't treat, that means because they interact, you can't treat the electrons one by one. You have to treat them all at once. So each electron can be everywhere. So the complexity of a problem to describe many electrons in a solid is, the number of places they can be, to the power of the number of electrons. And if you think about, that's what we call exponentially large number of numbers you need to know to characterize the state of the system. So the problem of, directly solving the equations for these many waves in a system is practically impossible. And so this is what I've been doing all my life. And but it's not so pessimistic, I hope to say at the end. And how long have I been going, David? I see I have a clock here, so about 10 minutes, 15, 10 or 15. Okay. So this is a lovely scene. I think maybe many of you know this movie, but maybe I loved it especially. So this is a scene from what I call the blackboard scene from the Coen brothers movie, A Serious Man. This is Professor Larry at the front of the room writing equations on a blackboard. And at the end, he concludes, and that proves we can't understand anything, okay? So, but that's not the right conclusion. We can understand things. We can make progress. And I'll talk about the nature of that progress as I go along. So I've tried to say that solving the quantum mechanics of many electrons in crystal, which is the simplest type of matter, and an important type of matter with special properties, is essentially impossible to do it directly without any approximation. Just because the wave functions for many particles is just too much information. Now, the problem that that I've dealt with all of my adult life is nature selects for us. For example, if the temperature is low, nature will select for us the lowest energy state of the matter. So the problem of understanding the properties of material at any given temperature is understanding what is the lowest energy quantum state I can make for these many electrons. And, or, not necessarily the lowest, but the low energy excitations, low energy quantum states determine the physical properties. And we want to know, what's the wave function for the low energy states and what properties do those wave functions apply. So tomorrow, some of you may be able to go to a lecture, the other public lecture in this series by Travis Humble, who will talk about the quest of building a quantum computer, which takes this problem and flips it on its head. They say, quantum wave functions in some situation have an enormous amount of information. Let's use that to compute in different ways. So these two almost opposite problems are obviously related to each other and feed off each other nowadays. Okay, so this this field, quantum theory of materials, in many ways is a subject. It really started during the Second World War or after the Second World War, or maybe a little bit before. And it's very much, for many years, the most important institution in this field was Bell Telephone Laboratories in Murray Hill, New Jersey, before we decided to break up Mother Bell back in the 80s. And, maybe the most important person, I'll come back to him later, probably in the history of Bell Labs, or one of the most important, is John Bardeen, who was involved not only in understanding the quantum physics that led to transistors and semiconductor technology, but also explaining another strange quantum phenomena, superconductivity, that I'll refer to in my talk, which was, when he did this, it was a mystery that had existed for 50 years and had, like most ununderstood things in science, there are a zillion explanations, but usually when the right one comes around, people will recognize that it's right. So Bardeen explains superconductivity. Another one more close to the present day is Phil Anderson, and I want to recommend to you this nice biography of Phil Anderson if you feel like some extra reading, written by Andy Zangwill at Georgia Tech University, and gives you some very nice insights into this field. So that was, 1980. And like a lot of things, actually, Westinghouse Research Labs here in Pittsburgh also played an important role in this subject. But nowadays, it's pretty much up to the universities to and the national labs around the world to keep this going. And I want to say, who is Phil Anderson? Phil Anderson is just some kid born in Crawford, Indiana. Actually, it's not quite right. His father was a professor at the University of Illinois. But to the younger people and high school students and younger who are here, science is done by ordinary people. And here's one very ordinary person. That's me, actually. And I somehow, ended up doing this with my life. My parents were not scientists. My father sold cars, similar to the one behind him. And my mother, wrote poetry. So I had absolutely no science background at all. And some of you are, have an opportunity to come to a place like this and learn about, learn about many different fields of science. That's a great opportunity I never had. And I think many of you are the people that are going to make the discoveries of the future. And as I hope to emphasize, what makes science fun is we're always learning new things, okay? So this is me sometimes later. This is actually a very typical scientific scene. And, it's the reason why we should, in this country, stick with our traditions and welcome scientific talent from all over the world to come here and create new knowledge. This is actually a photo taking in Zurich, Switzerland, I just discovered recently. This is my guy who was teaching me, who is Irish. And my friend Kazuo Ueda, who's Japanese, and me from Canada. And, I think if you go to any scientific meeting and have 6 people around a table, there's probably 4 or 5 different countries that are represented. So every bit of science is done by ordinary people, and it's very important that science have continuous support, because it's a delicate and from the point of view of something to do with your life, you only do it if you have to, because it's not the most practical choice. Okay, so now I'm going to let's see. Now I'm going to try and explain some examples of the quantum physics of matter, some of the surprises people have discovered over recent years. And the first example I'm going to give is something we call the fractional quantum Hall effect. And I'm claiming here that it's an example of emergence. It's something we see very often in quantum physics, and I'll explain what it is. Okay, so first thing I want to say is quantum Hall effect was discovered, was a property of nature, amazing property of nature that was discovered only because people made a new kind of material. And the kind of material that that they made was a very thin layers of perfectly ordered semiconductors. And it was actually made by a materials preparation technique called molecular beam epitaxy, represented in cartoon form here. And, what happens with this technique is that you more or less, with restrictions, lay down the atoms of this material one by one. And you can make a semiconductor of one type and surround it by another type of material. And the electrons will, as I said before, nature selects for us the states that have low energy. So the energies will, electrons will go to wherever they have lowest energy. They always go downhill. And so you can make it so that they'll lie in what we thought at the time was a very thin piece of matter. Okay, so these two-dimensional electron systems, people started to make sometime around 1970s, maybe, and they just got better and better at it for a long time. And as they started to make these materials, they discovered unexpected things. This happens every time, okay? Every time you make a new material, you discover unexpected things. And, the first thing I'm going to talk about that they discovered were special properties that happen when I have electron confined to a plane, to a two-dimensional space, as David was saying. Two-dimension means you can only go left and right or up and down. So this screen here is a good representation of a two-dimensional space, like in a thin film. So I'm not challenged to do a sophisticated piece of illustration. So this is representing an electron. And the special thing that happened was when they discovered was when they take these two-dimensional electrons and put them in a magnetic field. Now, many of you may know that when you have a charged particle in a magnetic field and it moves, it experiences a special type of force called a Lorentz force. The Lorentz force is perpendicular to the direction of motion, just like the Earth moving around the sun experience a force towards the sun, which is a perpendicular force. So these Lorentz forces bend the electrons around in orbits. These are called cyclotron orbits. And from the point of view of quantum mechanics, they're very similar to the orbits of electrons in an atom. And these orbits can be, have a center anywhere in the plane. But for a given center, they can have different velocities. If they have a bigger velocity, they go around in a bigger circle. But it turns out if you crunch the math, it takes the same time to go around a circle, no matter what its energy is. And that's actually the basis of one of the original ways of making high-energy particles called cyclotrons. And that's where this name comes from. That's the cyclotron orbit. Quantum mechanically, the energy in a cyclotron orbit, energy is velocity squared times mass in physics, and the energy in this orbit is quantized, okay? And we call the quanta of energy, the sets of states that have a given quantum of energy named after the person who first realized that this happened, Mr. Lev Landau. They're called Landau levels. Now, for each Landau level, there are many states. And because the cyclotron orbit can be many places. And it turns out that the number of states with a given quantized kinetic energy is equal to the number of flux quanta of magnetic field. So it turns out everything in quantum mechanics is quantized, and when you have a magnetic field piercing a two-dimensional film, that's what we call magnetic flux, and there's a quantum unit of that magnetic flux, And it turns out the number of states in Landau level is the number equal to the number of flux quanta. So we need to do a second lesson in quantum mechanics to explain about flux quanta, but you can imagine that this is true just because the cyclotron orbit can be many places. Okay, so this is, electron in a Landau level. They all have the same kinetic energy. And the kinetic energy is a property of one electron at a time. But electrons interact, as I mentioned before, with Coulomb interactions. Coulomb interactions means you can't treat one electron at a time. And we know from all of our experience with condensed matter physics that is when the interaction energy is much bigger than the energy separation between different kinetic energies, that's when interesting things happen. Okay, so this is the first time it was possible to do experiments where you could change because these are 2D systems, you can take electrons in and out of the 2D system by moving to the third dimension. That's something we call a capacitor, basically. And so as you change the number of electrons or change the magnetic field, you can change how many Landau levels are filled. And you can make a Landau level that's partially filled. And this had never been possible before. And what people discovered, I'll tell you in two steps, totally unexpected prior to experiment. I'm a theorist, and I have to say that's usually the way it goes. Things are discovered in experiment, and then we try and figure out why it happened, but not always. Okay, so this illustration illustrates some of the interesting things that happen when you have two-dimensional electrons in a magnetic field that's partially filled. The little yellow arrows, this is actually a illustration I should have noted here from a paper by a French scientist by the name of Christian Gladley that was published in Science magazine a few years ago. And the little yellow arrows represent our pictorial representation of flux quanta. And so in this system, what was discovered experimentally is that when you have 3 flux quanta for every electron, which means that the number of electrons is 1/3 the number of flux quanta, or we would say the Landau level is 1/3 filled. Then there's a special quantum state, a single quantum state that has the lowest energy, that's separated by an energy gap from all other quantum states. That's what we call an insulator. Okay, when there's an energy gap in a system, the system is quantum mechanically stuck, and there's no way for an electric field to move charge through the system. So for 1/3 fill Landau level, the system is an insulator, but it turns out it's a special kind of insulator because these cyclotron orbits that I've tried to indicate here, whoops, they're going this way, in the center, it turns out that and this is actually connected to the fact that the number of these orbits is proportional to the magnetic field, that there are always states at the edge of the system that are chiral. They move around the edge. So the end result of this physics, this part of it anyway, is that in a 2D system, when you make one of these insulators, it's just like a giant atom. Okay, no matter how big it is, it looks like one giant atom, and you can actually, attach electrical leads at some point along the edge, and the electrons would just move to another point along the edge through this basically giant atomic orbital. And there's that process, because the energies are quantized, there's no dissipation, no energy is lost. Normally, when you put electrical current through a metal, the metal heats up, and that's because energy is being transferred into heat. So what we always want conductors that don't have resistance are rather special. And so, yeah. So I'm saying, by the way, that I've been going for 30 minutes. So tell me if I'm wrong. So, so there's another type of state of matter that I referred to earlier as a superconductor. Superconductors have been known for 100 years, roughly, a little bit more than 100 years. The 100th year anniversary of superconductivity. One of the most amazing quantum phenomena in nature was just recognized relatively recently. This picture here is a picture of the Dutch scientist who first observed resistivity, observed superconductivity. He observed that when he cooled, what was this, mercury, if I remember correctly, to a low temperature, something very special happens. Over a temperature interval, which is, at around 10 degrees, over a temperature interval that's smaller than you can measure, the resistance, that means the heat produced by running a current, goes from a value that's typical for a metal to a value that's so small you can't measure it. In fact, in a superconductor, if you make a ring of a superconductor and start a current in it, then that current will flow for a time much longer than the age of the universe. And so that really nothing slows down these electrons. Not understood at all for roughly 50 years, almost 50 years, until the man at the left here, John Bardeen, and his postdoc and student, Cooper and Schrieffer, explained it, okay? This is the thing we would all like to do every day when we get up, when I have my PQI cup of Americano. And, it's still early. I still hope to do something like that during the day. But doesn't usually happen. Let me just mention the people on the bottom here. When I was in graduate school, one of the things I learned was that it was impossible for superconductivity to occur above around 25 Kelvin. People argued about whether it was 25 Kelvin or 30 Kelvin, but we were all taught that there was an upper limit of the temperature at which this occurred. And in 1986, these Swiss scientists, Bednorz and Mueller, discovered a material in which superconductivity, the same complete loss of electrical resistance, occurs at a temperature that is halfway to room temperature. I'll come back to that in a moment, okay? So why does superconductivity happen? So it's actually, you can state it rather quickly, and here I've stated it as, ABC. Three things you need to know to understand more or less what superconductivity is. First is that in quantum physics, this is actually, when we have quantum physics in matter, temperature always plays a role. You're never at absolutely zero temperature, and so temperature always plays a role. And so it's really what we call quantum statistical physics. And in quantum statistical physics, with first, most important dividing line is that there are two types of particles, fermions and bosons. Fermions are the uninteresting kind, or less interesting kind, and they satisfy something that those of you who have taken a high school chemistry class know, something called the Pauli exclusion principle, same Pauli. Exclusion principle says you can only put one quantum particle in a state, okay? And but the other type of particle says I'm allowed to, bosons, example of a boson is a quantum of light, a photon, and bosons you can put any number in a state. Okay. And so what superconductivity is really is that, superconductivity is something that happens when you put a whole bunch of charged particles into the same wave function. And so it can only happen with bosons, but electrons are fermions. But if you can get electrons to stick together in pairs, it turns out a pair of fermions becomes a boson, and these so-called Cooper pairs, after Bardeen's postdoc, Lionel Cooper, are bosons, and they Bose-condense. So that's what a superconductor is. It's a case where you have a bunch of electron pairs, Cooper pairs, and they're all in the same state. So there's only, even though you have many electrons, there's only one wave function. And it turns out that, the way electrical resistance happens is that the electrons scatter off a nucleus, let's say, and they transfer energy to the nucleus. That becomes heat. They scatter off a nucleus and give energy to it. But if you have many electrons, it turns out that scattering, the interaction between the electron and the neutrons, you can't change every electron at one time. So a quantum state with many bosons in the same state lives forever, more or less. Okay. So this is a quest. This is actually an important quest of quantum materials. Someday there will be a room temperature superconductor, and it actually, doesn't mean electricity will be free, but it will be very enabling for green technology, because it will be possible to move electricity through superconducting wires from one place to another without losing any of the energy, which is extremely important for green technology. Okay, so I think am I at 40 minutes? I have 5 minutes left? Yeah. Okay, so, this just shows how much progress we've made. Minus 273 C, I think you all know this is what we call absolute zero. That's when the quantum state prepared by nature is the lowest energy state. And superconductivity survives nowadays up to well over halfway to room temperature in this one material. And there are many ways to put materials together, and surely we will have a room temperature superconductor, hopefully in your life, and hopefully discovered by one of you. Okay. Okay, so this is my last topic. This is a recent topic. This is the one that's closest to my research. It's about something called moire materials. Nowadays, when we do quantum theory of materials, we're not so much trying to explain what happens in naturally occurring crystals, but we're trying to say, how can we put matter together to get properties that we want? And this is one axis along which this has been very successful. So I mentioned before that, quantum Hall effect started was because we learned to make very thin films of superconductors, only about 5 or 10 nanometers, 5 or 10 millionths of a meter thick. Things have improved since then. We now know how to isolate really two-dimensional crystals that are one atom or one molecule thick. In the case of so-called graphene, which is a crystal that lives in 2 dimensions and just a bunch of carbon atoms on a lattice, it's roughly, let's say, a third of a billionth of a meter thick. Okay, so let's say 100 times thicker or so, thinner than what we had before. And there's something special we can do with this. On the right-hand side here, this is a picture of 2 lattices of carbon atoms, 2 what we call graphene sheets, overlaid with a small difference in their orientation. And you may be familiar with moire patterns. They arise many times. If you take any regular pattern and overlay it with another one that's slightly different, you'll get kind of a spatial beating pattern in which the way in which one layer sits on top of the other changes slowly in space. Okay, that's a moire pattern. And you can see here, the twist makes a moire pattern in the graphene. And the amazing thing, and really to explain this, I'd have to do quantum mechanics 3, but it turns out the properties of electrons in this, moire system, which you can engineer, they look like a crystal. They're like those of a crystal, but a crystal that has the period of the moire pattern. And the moire pattern period is typically, 10, 20 nanometers. So we can actually make 2D crystals that effectively have giant atoms, okay? Giant atoms. And that's the reason giant atoms are important, is because I mentioned the so-called field effect before. You can move electrons in and out of a 2D conducting plane. That's how transistors work. But there's a limit on how many electrons you can move. And it turns out that limit is roughly 1 for every 10,000. 1 electron can be moved into a 2D layer for every 10,000 atoms or so without everything falling apart. But now, in these moire systems, we made the atoms 10,000 times bigger. And so you can change the number of electrons per atom in these systems. So they're just by changing a voltage in an electrical apparatus. And number of electrons per atom is what you change when you move through the periodic table. So this, allows us to study phenomena in crystals with a new level of control. And what I'm trying to say here, just about everything we know, this is like a table of contents for a course on the type of quantum theory I'm talking about. And everything that's been seen in atomic scale crystals has been seen in these moire materials, including one thing at the bottom of this list, which is called the anomalous fractional quantum Hall effect, which has only been seen so far in moire materials. This will change eventually. But what is the anomalous quantum Hall effect? So turns out the quantum Hall effect that I was talking about before, associated with particles moving around in cyclotron orbits because of Lorentz forces due to a magnetic field, we can make systems in which that happens without a magnetic field. The source of the effective Lorentz force is something called Berry phases, it's connected to the geometry of the quantum state in real space, and the geometry of the quantum state is function of its momentum, and it turns out that can give an effective Lorentz force, so that these insulating states in which there are electrons that move around the edge can occur with and without a magnetic field. And there's one thing in that cartoon of the fractional quantum Hall effect I showed you before that I didn't remember to point to, and that is that when you have a state which is 1 electron, for every 3 flux quantum, if you add an extra electron in those systems, it turns out they split into 1/3 charge. So these systems, we can have fractional charges as elementary excitations without a magnetic field. Okay, so now, David, I'm ending, but I want to say 2 things about the nature of the quantum science that I've done all my life. Okay, so what I've copied here is a paraphrase of a remark made by Martin Schwarzschild. It's actually was a remark he made about the field he worked in, which was stellar evolution, the life cycle of stars, which people, beautiful subject people came to understand. He was pretty well, and he was an important contributor. And what he says here is, left on its own, theory, he was also a theorist, is prone to stray. And so that's how we make progress in this subject. And that's what makes it so delightful every day, that the way we make progress is we have an idea. We're usually not really sure if we're seeing something really new, if it's the right idea. So somebody has to do an experiment to see if that idea is right. And the interplay back and forth between people like me and people like Ben Hunt and people like David Snoke is really exciting and delightful, and generates, we know from experience, new knowledge. Okay, so theory. There is a virtuous interplay between theory and experiment, using different specialized expertise that allows we as a community to make progress. Okay. And finally, I want to say, this is a quote from Richard Feynman, a very famous physicist. Most of you have probably heard of him. He was on the Challenger inquiry a number of years ago, and made many, many important contributions to quantum physics. And he started to think a long, long time ago, when people, the semiconductor revolution was just starting. People were starting to get very proud about the miniaturizations that they could achieve. And he said, haven't really started. What if we could control the structure of matter atom by atom? And in physics and in chemistry and in biomaterials and in many other fields, we're along different axes. We're coming closer and closer to this ability to make matter as we like, one atom at a time, and to really engineer fantastic properties of materials. And so this subject is just accelerating as these techniques improve. So I think I've got a couple of minutes over, but I'll stop right here.
Thank you so much, Dr. MacDonald. We are going to go ahead and open the floor up to questions. If you have a question, please raise your hand, and one of our two lovely mic runners at each end of the theater will bring a microphone to you. Please speak into the microphone so our presenter, as well as the rest of the audience members, can hear your question. We have about 10 or 15 minutes for questions. So, who's up first? Here.
Thank you. Similarly to the quotes that you had on the screen today, has there something that your colleagues or yourself have said recently that was either entertaining or wildly incorrect a couple of years later, or something memorable?
Yeah. So are you asking, have I ever been wrong? As I said, the theory side of materials, it's not like some areas of quantum physics where there are, very sophisticated, very highly technical methods that if you master, you can solve any problem. That's not true about my subject. So guessing is acceptable in my subject, and guesses can be proven wrong. So it's still possible. It still makes progress. Okay, I actually try not to be wrong very often, but but I have been wrong. I can't think of an example. Very rare. And the way it works is, even when you're wrong, you hope for 5 more years that somehow you're right. So, yeah, great question.
I see one in the back. Sorry, forgive us. We've got a lot of... We're going to ask you to use the mic just so everyone down here can hear you.
How's that? Is that good? Yeah, I can hear you.
So
I can't see you, but I can hear you.
if taking two layers of graphene and twisting them slightly creates a new quantum behavior, should we be taking like other thin layers of different types of atoms and just twisting them and seeing what happens? I mean, is that
Yeah, so I'm not sure what your day job is, but that's exactly the right thing to do. And people have been doing that. And, the checklist of phenomena that people have observed is not only graphene systems, but the other class of systems where people have made most progress are so-called transition metal dichalcogenides. So that's, combinations of a metal and things like, sulfur or selenium. So it turns out that they form, naturally in the bulk, they make crystals in which the chemical bonding between different layers is extremely weak. So it's very easy to, as people say, cleave them, separate off layer by layer and study the properties of layers. So it's not only that. I think the set of materials where this playbook of making, these moire materials, works very well is probably not going to be extremely large, but we already have, the transition metal dichalcogenide family involves, perhaps up to about 10 materials. And if you talk about different ways you can layer them, the set of things to explore has hardly been touched in the community, even though people are thinking exactly in your direction.
Interesting. Thank you.
Masoul, there's one right below you. Below you a few rows. Oh, okay.
Okay, thank you so much for the lecture.
Thank you.
If you can share with us your beginnings in this field of 2D materials, like your personal story, and if you can give us an advice for young physicists.
Yeah, I'm not sure. So here's my story in science. I did a PhD. Okay, I was actually working on magnetism and metals. And then I was a postdoc. I actually had 2 kids. Wasn't clear I was going to get, to the next level of actually having a job in a laboratory or university. And I actually, this is one of the pivotal moments in my life. I worked at a government lab in Canada, and I kept begging my bosses to hire me because I knew in a government lab, it's possible. They could just decide to hire you, but they decided not to hire me. And I actually accepted a position to teach physics in Lesotho in southern Africa. And I was going there, and, then they found a local person to do it, so they said they didn't want me either. And so, just around then, my bosses had been said I didn't know enough. I should, get a little more experience before they hired me. And so they did hire me, but they sent me away to get more experience. And that's how I ended up in Zurich, Switzerland. Morris Rice was somebody who had just come from Bell Labs as it was starting to break out. And the experience I got by interacting with him, I think, was one of the big breaks I got in my scientific life. So, everybody has their own journey. In terms of doing science, I think the important thing is to be patient, to try to do something new, but whenever you do, think about it deeply until you understand it completely, and you never lose that understanding, and you can build on it. So I think that's, I think most of us would say, who here in the room are scientists, would say that our careers are built on, a half a dozen things that we have thought about more than nearly anybody else. And so that gives you an opportunity to make a contribution when the right thing comes around.
Okay, I am not a physicist. I am a librarian. So I hope this
Okay.
is not a dumb question.
Where are you?
I'm right over here.
Okay, yeah. My daughter's a librarian. So.
Oh, good. I feel better. Okay. I always sort of assumed that first and second dimensions were almost sort of more of a mathematical concept. So these thin sheets, I mean, do they really exist in the second dimension? Is a single layer of atom considered two-dimensional?
When we say, when we say two-dimensional, there's a very precise meaning that we have, and it's connected to quantum mechanics. So it turns out when things are thin enough, and sometimes in semiconductors, the type of system I mentioned at the beginning, even 10 nanometers is thin enough. When we say two-dimensional, we mean that the quantum state that the electrons have, which involves the possibility of, the wave function the matter wave, varying in the third direction, that they're always stuck in the lowest energy state for that motion. So because every electron shares the same third dimension wave character, you can forget about it. It turns out mathematically it's exactly true that you can forget about it. Yeah, so viewing these systems as two-dimensional is exactly right. Up to, let's say 10,000 degrees Kelvin, and we don't care about that.
We have another question up here.
The use of AI or quantum computers as a helpful tool. Over this way.
Okay. Yeah. Go ahead. I can hear you.
AI and quantum computing, can they solve superconductivity to room temperature, or what's the use of them in your field?
Yeah, so AI will probably is a tool. People will learn to use it. Generally speaking, AI is a good interpolator, not so great an extrapolator. The properties, part of this immense complication of physical property, quantum systems with many degrees of freedom, means that it's very hard. And so far, it hasn't really been useful for any, for most of the central materials problem. You mentioned, for example, high temperature superconductivity, room temperature superconductivity. Another important problem is having a solid state electrolyte, making all the parts of a battery solid. That would be much better. Then you wouldn't have to take the battery out of your smart suitcase when you get on the plane. This turns out it's not good. It's liquid. It means it might start burning. So Google actually decided that they would, try to use AI to find a material that was better solid-state electrolyte than anything we knew. And I've had 2 reports on this effort. Okay, one report I had, from different people, just a few days apart. One report was that Google discovered 58 materials. On further examination, none of them worked. Okay, and then I heard somebody who was on a committee with the manager of this project at Google, and he was explaining it as a great success. But the real truth is the first thing. It didn't work, and and it won't work for high temperature superconductivity either. The materials properties that you're interested in just depends so sensitively on things that the learning, the training, AI training, network training might not recognize as being important. So far, we haven't learned to make useful predictions. For some more routine problems, like, for example, one of the great successes is just knowing the total energy of a system as a function of the positions of all of the centers of all the atom, all the nuclei. So in my field, so that's now routinely done by training, training a neural net by using machine learning methods, and it works very, very well. And the reason is that the energy as a bunch of atoms depends very smoothly on where the atoms are, and so we have to find out what problems it's good for. It certainly is. Many people have discovered it's good for doing literature searches, as long as you don't believe everything it tells you. Yeah.
Do we have
Great
any
question.
other questions? Wave those hands so we can see you. Oh, I see one over here.
Well, just a basic question to maybe shed some light on the 2D. So if you had this film and you had some kind of ball that it would probably have to be small, but if you then took the film and you put it on top of the ball so that it's not curved a whole lot, it would probably still be 2D based on your wave function all being in the lowest level. And so to describe the whole thing, it's still 3D, but quantum mechanically would be 2D. But then there would be a point where you're wrapping it too tight, I guess, and you hit some limit.
So for just a stone, that probably wouldn't work because you can't make it, control its geometry so well. Something very complicated would happen, but something very similar to what you're saying happens. And, in this 2D world, part of the richness is making multi-layers. So you make one 2D layer, and then you can put another 2D layer on top of it, and they all talk to each other quantum mechanically. And that, if you like, design axis is very important for getting new types of properties. So it works when you put a 2D material on a 2D material. If your stone is 2D, it works.
Right. We're up. There we go. Okay, one moment.
With superconductivity, has any experience been used in a vacuum about using that as part of, say, a maglev in the case of, say, using it on the moon or Mars for transportation, since it's already a vacuum and cold, instead of using like liquid nitrogen here on Earth to move it back and forth?
Yeah, so does anybody else know that? I suspect that building the vacuum system would be expensive. As you know, there are working maglev trains. I guess the largest ones are in Japan, if I remember correctly. And whether it's the best way to build a transportation system is an economic question. And if we had a room temperature superconductor, in other words, if we didn't require the tremendous expense of having to arrange to cool the superconducting elements, then I think it's very likely that magnetic levitation would be widely used in transportation technology. Many things like that. Really cooling things on industrial scale is incredibly expensive. So the economic driver has to be very, very high. So room temperature is where we need to go.
Are we missing anyone else? Wave those hands. I don't see a hand. Oh, I see a hand over here. All right.
Hi, I loved your talk. I wanted to ask this question about what do you think in your career, there's been a lot of different types of rare phenomena that have happened. And there is this thing about what else is out there? What are you most excited about in terms of what is to come?
Yeah, so in my career, roughly every 5 to 10 years, something completely unexpected has come along. It's actually about time now for it to happen. So, unexpectedly today, the tariffs were delayed, or So maybe unexpectedly tomorrow we'll have, the most obvious quest is, something we know we want is a room temperature superconductor. There are, as many of you are aware, there have been fundamental physics, new fundamental physics understanding in just metallic magnets, which is, a subject that's thousands of years old. But we've understood things just in the last 10, 20 years, which is the reason, hard disks hold more and more information. That's ongoing. There's magnetism is actually a rather unique thing because it's a collective state of matter, a little bit harder to explain maybe than a superconductor, but it behaves collectively, is magnetic in the experience, are the words we would use, up to thousands of degrees Kelvin. So we have no problem with having magnetism at any order, and we're still learning to new ways to exploit that collective behavior. But I think things will be coming along that nobody knows even how to articulate. And of course, I work in some little corner of science. I love it, but it applies equally well to every field of science. You have a bunch of smart people trying to think of new things and talking to each other all across the world and exchanging ideas through the scientific literature. Wonderful things happen. Scientific progress has probably been more rapid since the Second World War than ever before in human history. It's almost scary how quickly we're learning new things. AI is one of them.
All right, I see. Do we see any other? Wave those hands so that we can see you. Oh, yep, you got it, Miss.
I'm a little early on in my journey of physics, but if we do get to the point where we can have room temperature, room temperature semiconductors, would this make it easier to build quantum computers at a scale? Because I know it's very limited by cooling systems.
Absolutely. So one of the technologies, as you know, for quantum computing is superconducting qubits, which depends on the collective quantum mechanics of these macroscopic wave functions I was talking about. And one of the, I think the biggest problems are with the actual qubits is the hardware, and the materials aren't perfect. And if we had, now people use aluminum because it's advantageous. Aluminum is a superconductor below 2 degrees Kelvin. It's very likely that if we had a room temperature superconductor, we could make everything much more robust and less sensitive to detail. So I think that's another direction. To build a quantum computer, I was talking to some other experts over dinner this evening, and I think everybody agrees we have to, in order to build a useful quantum computer, we have to learn things we don't know now. And where the progress will come from, it's hard to say. But if we had a room temperature superconductor that had good mechanical properties, that might do the trick. Yeah.
All right.
And so it's your job to discover it.
Okay, folks, is this on? Yes? Okay. We're going to go ahead. We're going to have to wrap up the questions there. Let's all give a very, very big round of applause.
Yeah, thanks, everybody. You've been really wonderful. Thank you.
And to PQI. And before you all peace out, Professor Snook would like to give a brief comment.
Yes, this is not why I'm standing up here, but I did forget to mention one other award that Allan got, which is he was named last year a citation laureate, which I think means you have as many citations as the Nobel Prize winner or something like that. So, but yeah, I just want to let you all know that tomorrow there's another public session. It's in the middle of the day. I know not everybody can get away in the middle of the day, But at 11:30 a.m., we're going to have a public talk by Travis Humble, who I think is here. I can't see in the dark. He is head of a quantum computing effort at Oak Ridge Laboratory. We'll be talking about unraveling the mysteries of quantum science and technology. Then there'll be a lunch break, and then from 1:30 to 3, there'll be 3 speakers, myself, Andrew Jordan, and Porter Williams, talking about how to think about quantum mechanics. And so we heard about the wave function today. So my talk is the wave function real? And then, all these have questions in their titles. So Andrew's talk will be, what is a quantum measurement? And then Porter Williams' talk, who's a philosopher, will be, what are the possible quantum worlds? So I encourage you all to come back if you can for that, and those are open to the public as well. So let's thank our Carnegie Science hosts. Thank you very much.